This is the beginning of the third video for 1D kinematics. This will be all about falling objects and gravity. One of the most common problems that we're going to see again and again for kinematics is free fall or projectile motion. Free fall is basically an object that's falling. Even if you throw it up, it's still in free fall, meaning that it only has the force of gravity acting upon it. For our metric system, you should know the acceleration on Earth when you're close to the surface, so around sea level, is 9.80 meters per second squared. But for all intents and purposes, it's so close to 10 that feel free to use 10 anytime, whether it's multiple choice or short response or math problem. Use 10 and it'll make your life a little bit easier. We'll get into it a little bit more in the 2 units from now when we talk about gravity and the force of gravity. But Galileo basically did a bunch of tests with ramps and started noticing that objects of different sizes and different masses and different shapes all started falling at roughly the same rate, so that he came up with the fundamental idea that no matter what the object is, in the absence of air resistance, they all fall to Earth at the same rate. Not the same speed, but at the same acceleration. They will change their speed at the same constant rate. As mentioned on the previous slide, free fall means that the object is only under the influence of gravitational forces. No air resistance, no drag, no tension rope pulling up. So whether you throw an object straight up, straight out, straight down, you release it, you throw it up on an angle like a baseball, it's all experiencing just the force of gravity. We're ignoring air resistance pretty much until we get to the energy unit. We might now have things like previous problems moving in 2 different directions. So maybe something was moving to the right, positive speed, positive velocity, but it was slowing down, so a left acceleration vector or negative acceleration. In this case, if we throw something upward, it would have a positive velocity, but gravity is always going to be coming down, always pointing towards the center of the Earth, so its vector might be negative if you have some things that are pointing upward. So your reference frame can be different than your lab partner or your friends and still get the same numerical magnitude, just opposite signs. Your reference frame is going to be the trickiest and hardest part to get used to. The way gravity works, for the most part, with kinematics, is every single second that it spends in the air, in the absence of air resistance, it'll get 9.8, or again roughly 10, meters per second faster. So within the first second it goes from 0 to 10, and then the next one it goes from 10 to 20, 20 to 30, etc. Same thing whether you're throwing it up or even up on an angle. If you throw something upward, it does have to slow down because the acceleration is pointing in the opposite direction. The upward velocity would reach 0, turn around and become a downward velocity, maybe negative, and get faster and faster and faster. So you can see these are your motion diagrams. Distances is getting smaller, it's slowing down. Distances are getting bigger, it's speeding up. So let's jump right in. Practice problem. You stand on the edge of a cliff that seems to have an endless drop. In other words, we're never going to hit the ground. If you release a pebble, how far has it fallen in 5.3 seconds? If you release a pebble, that means it's not going to have any forces acting on it other than gravity, which means your initial speed will be 0. So the first thing I would do is recognize that your initial speed is 0. How far is displacement, which is the change in y? Because we're dealing with the vertical plane, so does change of x. So I'm going to use the displacement with acceleration equation, where your initial position will be 0 and your initial velocity will be 0. If you recognize that the initial speed is 0, then what we do is we take this equation and we transform it into what's called the free fall equation, where the zeros remove some variables and all we're left with is y equals 1/2 at squared. You can use this equation anytime you want and still get full credit as long as you're dealing with an initial speed of 0. Plug in acceleration is 10, my time is 5.3. Yes, it is moving downward. So you could argue that it's negative 10, and that's fine. Your answer would be the exact same magnitude, except it would be a negative 140 meters instead of a positive 140 meters. If I said going down was positive, then I get a positive value because it moved downward. If I said going down was negative, then my acceleration would be negative 10, and my answer would be negative 140 meters. Still perfect score, perfect answer. Instead, what happens if we throw it upward, initially 11 meters per second? How long will it take to return to your hand? So if it goes upward, I'm going to say that's positive. That means gravity is coming down. That's going to be negative. When it returns to your hand, it's in the exact same starting position, which means the change in y will be 0. Coming down will be negative if it's going up is positive. If you haven't seen these before, that's just shorthand for therefore, 3 dots in a triangle. I'm using the same equation, just not the free fall equation, because the initial speed is 11, positive 11, not 0. The initial and final position, that will be the same, it'll be 0. Initial velocity is 11, I don't know my time. I know my acceleration would be negative 10 because it's pointing in the opposite direction than my initial velocity. Now I have a quadratic, and I'd have to solve that. If you have a TI-84 calculator or greater, you have an app on your calculator. It's usually number 8, and the app one is PLYSMLT2. When you get to it, it's called the polynomial root finder, and it will automatically solve the equation for you. Although there is a trick. Instead of doing that, if an object returns to the exact same vertical position as it originally did, it's a symmetrical problem, meaning if it took 10 seconds to go up, it'd take 10 seconds to go down. If we throw it upward at positive 11, it's going to come down at negative 11, negative meaning down. It's the exact same speed, just opposite direction, which means we can use our acceleration equation with the initial speed being 11, the final speed being negative 11, the acceleration being negative 10. Now I don't have to do the quadratic. If I do this, I get 2.2 seconds. It'd be 22 negative divided by negative 10, 2.2 seconds. If you did the quadratic over here, you would recognize that you would get the exact same answer. And in fact, remember for this quadratic, your algebra skills should tell you that you get 2 answers. One of them is probably going to be negative, and one will be positive. The positive will be 2.2, and the negative is just not plausible. It's not a reasonable answer. You're not going to throw something up, have it come back to your hand, and somehow lost time, negative time. So we're back to an edge. This time it has a 6-meter overhang. The ball is in your hand, and you throw it upward with an initial speed of 8. Your job is to answer the following questions. How long is the ball in the air? Now this one doesn't return to your hand, which means we can't use the symmetrical trick. It's going to go up, turn around, come back to us, and then keep falling that 6 meters all the way to the ground. So your initial speed is 8. It's going to go up, it's going to come back down. I'm going to say going up is positive. That means gravity is going to be negative 10, but my initial speed will be positive 8. That's A subscript y, A sub y, meaning the acceleration on the y-axis is negative 10, or gravity. I need an equation with time, where I know everything but one variable, which unfortunately would be the quadratic. The final position will be 0. The initial position will be 6. The initial velocity will be 8, positive because it's going up, but the acceleration will be negative 10 because it's coming down. You do have a quadratic. So again, you're not expected to do the quadratic formula, the negative b plus or minus the square root. You don't have to do that. Just use the calculator and let it solve it for you. You're not being tested on your algebra, although you have to do algebra to get the answer. When you use the calculator, you get 2 possibilities, negative 0.556 or 2.156. Now the difference is you can't have a negative time, so it's got to be the positive one. our answer is it's going to be in the air for 2.2 seconds. For part B, clear the screen and bring back up our pertinent information. Your job is to figure out how fast is it going when it hits the ground. So for B, I would use the acceleration equation. You know all three variables other than the one that you're solving for, which is the final velocity. Your initial velocity would be the positive 8, your acceleration would be the negative 10, and your time would be 2.2 seconds. Or we could also use the third kinematics equation, which is the velocity with constant acceleration. And I'm going to do both just to show you. Plugging in my positive 8, my negative 10, and my 2.2 seconds. Over here, I'm going to plug in my positive 8, which I'm going to square. Acceleration is negative 10, and this is the change in y. My initial position is going to be, final minus initial. My final position is a 0. That's a 0 because you're on the ground. But my initial position is positive 6 because I'm in the air 6 meters above the 0 point. So it's final minus initial, 0 minus 6. When you solve them, you get negative 14 meters per second. Now, technically with this one, it's not negative. I have to add in the negative because you can't take a square root and get a negative number because the negative just refers to the down. Not a number less than 0. It's a positive 14 going down. For part C, it's going to ask me what's the displacement. Well, the displacement is the final position minus the initial position. So the change in displacement is negative 6 meters, which you already saw us do if we happen to tackle part B with the third kinematics equation. For D, we're going to be talking about the total distance. So again, clean the board, bring back our pertinent information, our setup. So that ball is going to go up a certain distance. It's going to fall back to the original position of your hand, but then it's going to fall that extra 6 meters down to the ground. So I know this distance is 6, and I know that these two distances are going to be symmetrical. So I just got to figure out how to solve for those. So I'm going to use the same equation that I did on the previous part. I'm going to solve for the delta y. How high does it go from the start to the highest point? At the highest point, it turns around and comes back down. What's the speed at that instant you turn around? Hopefully your mind already answered that it was a 0. Anytime you turn around, your speed is 0. So at the highest point, I'm taking basically this orange arrow pointing up. Initial speed is 8. Final speed is 0. I'm solving for the change of y from here to here. Solve the equation, you get 3.2 meters. So it'll travel 3.2 meters from when I let go until it reaches the speed of 0 due to gravity, slowing it down, and then it's going to fall 3.2 meters back down, and then it's going to keep going the 6 meters down, add up those numbers with 2 digits to maintain the 2 sig figs up here, 12 meters. That's the end of the third video. Graphical analysis will be the fourth and final video. It might be a little long, but you can watch it in different parts if you need to.